Hello and welcome to our next video, third video of this unit, where we're going to go and revisit the errors that we discussed last semester. This one goes a little more in depth, but we will start with a quick review on these things here. So remember, there are two different types of errors that you can make because there's sort of two decisions that are made based off of your sample. You either reject the null hypothesis or fail to reject the null hypothesis. And so sometimes you can do those things incorrectly. So let's quickly remind ourselves of a type 1 versus a type 2 error. If you want to pause the video and sort of just write in what you think the answers are before I tell them to you, you can do that. I think it's a good idea. But otherwise, here we go. So a type 1 error is when the null hypothesis is true. Okay, so we failed to reject the null hypothesis in our test, but we mistakenly rejected it. So it turns out the null hypothesis is true, and we, from our sample, ended up rejecting it and saying that we don't think it's true. Type 2 error is sort of the flip to that. That's where our null hypothesis is false. So we should have rejected it. However, we fail to reject it. So whatever our sample is came out and we were like, oh, that's close enough. But it turns out that we should have rejected it, that the null hypothesis is actually false. So let's take an example of that and sort of define what that means here. So for our example, we're going to think about flu vaccines. You know, you're supposed to get the flu shot every year. Fun fact though, these flu shots, they're like kind of curated every year, and they can have different efficacy rates. Maybe you've heard about this in the news, is that sometimes they say, oh, the flu shot is not particularly good this year, or is really good, or whatever. And so that's what efficacy sort of is. So as you can see there, like there's sometimes as low as 10% and as high as 60%. And what efficacy really means is that it prevented the illness that percentage of the time. So on average, over the course of many, many years, they have figured out that the approximate efficacy rate is 45%. And so every year they're trying to improve upon that 45%, obviously, and make it even better. You know, there's, as we can saw above there, like there are years where it's 60%. So let's talk about what the errors would be here. Before we do that, we have to define our hypotheses here. So take a quick moment to think about what are our different hypotheses for this. And so for the null hypothesis, it would be that we believe the proportion of efficacy or proportion of individuals that are getting their illness prevented is 45% or 0.45. And our goal every year is to try to make that better. So we want a higher efficacy rate. And so that's where P is the proportion of individuals that the vaccine prevented illness. That's what our P will mean here. Or there are other ways to phrase that, but that's sort of the idea, is like what proportion of people that got this shot actually got some prevention happening from there. So what would be a type 1 and a type 2 error in this scenario? I'm going to leave that to you, okay? You're going to go ahead and take a pause and try to answer what these are and see if you can jot down what are some consequences for those sorts of errors. So review the definitions up above. Take a moment. When you get into class, you're going to do a quick share with a partner. Now, what we did not talk about last semester, so everything so far, hopefully you're sort of like, that seems like, I don't know, just review. Great, that's exactly where you should be. What we haven't talked about is sort of, what's the chances of making these errors? That's always something you want to know about, is like, all right, if I know these errors exist, what's the probability that I actually do make these errors, you know? Because obviously you want to shrinkify chances of making any of these errors. And so we're going to talk a little bit about that after this. So let's talk about this. What's the likelihood of making a type 1 error? Remember, that is when we reject the null hypothesis, and we were not supposed to. So what's the chances of something like that happening? Well, if you think about it, this is a case where the null is true, but we just got a really unlucky sample that was just far enough away from the true null by chance. So that means that the p-value has fallen below our alpha level. Remember, the alpha level is the significance level. So we got a p-value that's just a skosh below, or maybe a skosh, maybe a lot below, the alpha level that we have set, and that wasn't supposed to be the case. So the chance that we make a type 1 error actually is exactly equal to whatever you set for your alpha. So the chances of making a type 1 error is equivalent to the alpha level, okay? So you're in total control of that. That's really cool. So the chances of making a type 1 error is something that is under your control for all of this. So let's sort of just, visually sort of see what's going on here. So, for example, all of these are different sort of distributions, sampling distributions that are all centered at 0.45, because I'm going back to that vaccine context from before here. So that we have here different alpha levels that are set for us and we can sort of see. So if we were to grab a sample of people to check efficacy and we got their, I'm gonna use a different color here. Got them to show up in this, is yellow on my page. You have a different colored paper that the yellow is not really showing up. But if you got a sample where the efficacy rate shows up somewhere in that yellow region there, that's a scenario of where actually the population is centered at 45% and you just got a sample that's somewhere in here. As it turns out, if you sort of do the math kind of working backwards, the cutoff here that you see is at 0.495. So if you end up with a sample where the efficacy rate is higher than 0.495, then you end up saying like, oh, I reject the null hypothesis, but that wasn't the case. It's actually true that it's still centered at 45%. And this would happen out an alpha level of 0.10. All right, what if we were stricter, though, and went to an alpha level of 0.05? That means our cutoff right here, so 0.05, is going to be at 0.508 this time around. Notice that that area has shrunk a bit. And then here, we can even go tighter and more strict, 0.01. So that's going to be there at a cutoff of 0.532. So you can see that we have this control because we are setting the alpha level for ourselves before we even run these tests. And so we have the control over how often we make a type 1 error. All right, but let's think about the flip side to this. What's the chances of making a type 2 error? A type 2 error. Okay, well, that's when the null is false, but we failed to reject it. So the null is actually false, but we have no evidence to say it's not true. Okay, so what we do is we actually denote this with another Greek letter, like you have the alpha from above here. They decide to stick with the flavor there and just move along in the Greek letter alphabet. Beta is the Greek letter we use to represent the probability of making a type 2 error. So just like with the type 1 error, this is also from an unlucky sample. Anytime you make these types of errors, it's because you got a quote-unquote unlucky sample. But now, in the sense that what we got is that it's now in the sense that it is far from the true center, but close enough to the null. So to keep this in mind, that what this means is that the population should be actually centered elsewhere. We thought it was centered at, in this case, 45%. But what if this new vaccine we come up with is like the true center is further away? It's like, 50%, 60%. Well, it means that we just got an unlucky sample from that distribution. And it just so happens that it's actually kind of close to the original, what we thought was the true distribution. It's a little tough, and we'll try to talk about this more in class. But like here, we'll look at this again. So I'm going to mark these again. These are the centers of what is our null distribution, still 45%, okay? The other curves you're seeing there are actually the alternative, that is the true, these are where they're truly supposed to be, the true sampling distribution, not what we thought was true about the past, okay? I should finish up this paragraph here. So like there are a lot of different like possible alternative models. So that's what we're going to talk about down here. So like what is the true center supposed to be? Like there's a lot of different ways. It could change from year to year. And so it can be tough to actually know that for many, many reasons. And so if we don't know the true value, then sometimes we might sort of like take a guess. So we may never actually be able to calculate the true value of beta. But what we'll sort of find out in the future is like maybe we can take a strong guess at it or think hypothetically about it if it is true that it's centered. So here we'll talk about the center of our true distribution. So we in the past have said 45%. Well, here, what if in fact our sampling distribution is truly centered over further to the right at, let's say, 55%. Okay, well then what's the chances that we end up grabbing a sample and it's not far enough away from the old null hypothesis, well, I'm going to call it P naught, at 45%. That is this blue shaded region right here that I'm for some reason outlining in red. That's the blue shaded region there. That is going to be our type 2 error. So this is our type 2 error. The yellow is still the possibility of making a type 1 error there. So this corresponds actually with the above aforementioned, like the 0.508 in the second example up above. So anything from that blue region, it's possible to get where it's just too close to the null hypothesis center, in which we would go like, well, that's not far enough away. But it turned out it's just an unlucky pull from this distribution here, which I should actually go over in green instead. So this distribution here, so we're grabbing actually a sample that actually is from this sampling distribution, which is centered at 55%. But if it's in this blue region, it's just too close to the null center. But you can see how you can shrinkify the possibility of making that type of error by if it turns out your null center is actually, your true center is much further to the right in this case. So in this case, on the right here, our center for the true efficacy rate is at 0.58, 58%. So now the chances of getting something that is still too close to our null thought is much smaller. See in this blue region here, that's still the probability of making a type 2 error, and it has shrunk a lot because the true center is much further away from the null center. I hope me saying true and null like that so much is like really making sense to you. So here's the thing though, is that, we are hypothetically thinking about these sampling distributions that are centered so much further away. You often don't know. That makes the type 2 error so difficult to really know what is the probability of doing that, is because it requires you to know what the universe knows, which is where is the true center for the sampling distribution. And that's usually something we don't know. That's why actually we do these tests. And then we'll talk about in the coming weeks something called confidence intervals, where we try to think about what is the true center, but we'll never actually know. We might be pretty sure, but we'll never actually know. All right, so that's the likelihood here. So alpha, totally under our control. Type 1 error, we are in control of that. The type 2 error, less control over that. So let's take a look at sort of then reducing these. So As with every single error that gets made, you want to reduce the chances of making that error. How do you do this? So reducing the chance of making these types of errors, let's start with a type 1 error. So since the type 1 error, the likelihood of making that is just alpha, which is under our control, then the easiest thing we can do is just select a smaller alpha level, which would make it harder to get a p-value that rejects the null hypothesis. So in our situation for this flu vaccine, this would mean what? If we were to try to reduce the type of, or making a type 1 error, what would it mean we'd have to do? Well, what it would mean is that we would have to sort of set our bar a bit higher. So it would mean raising the efficacy level that we deem, we'll put this in quotes, especially effective. So we'd want to just sort of like, it's at, if we're thinking 45%, you know, and we were going, oh, if it shows 48, that'd be cool. But you might go like, let's just click it up to 50. If it shows 50, then you're going to reduce the chance of accidentally rejecting the null hypothesis. And that's important. You want to make sure that you don't accidentally reject the null hypothesis in this case. Because if we reject the null hypothesis on accident, what it's going to mean is that we have a vaccine that actually is not particularly effective. So if we sort of set our bar a bit higher, it's like, all right, you need to show me at least 50, 51%. Then we know that we probably didn't get it just by chance. So the probability of just getting an unlucky sample starts to shrink for us. And that's really important. So here's an example of what we're talking about here with our sort of hypothetical thing. So each of these have a null center at 45. And we have then the alternative center, or the true center, we'll say at 58%. Let's say hypothetically this new vaccine has a 58% efficacy rate. So in this particular case, we can sort of look at how changing the alpha level changes our probability of making a type 1 error. So here, this is at an alpha level of 0.05. And so you can see that yellow area here, that represents the probability of making this type 1 error, where we would reject and we weren't supposed to. While if we change the alpha level to 1%, now you can see that that area is much smaller there. However, there's a drawback to this. You can't just willy-nilly go like, great, I'm just going to make sure all my alpha levels are super tiny, because notice what happened with that blue shading. Do you remember what the blue shading represents? The blue shading represents the probability of making a type 2 error. So when you shrink your alpha level, you now have a greater chance of making a type 2 error. Bummer. If you thought that was just a quick fix, you're wrong. Okay, so I think that helps us now understand a little bit about how we might be able to avoid making a type 2 error. So if shrinking the alpha level makes the chance of a type 2 go up, then selecting, we're going to shrink down here for like, selecting a larger alpha level will make it a shrink for the type 2 error, okay? So in other words, like this makes it easier for us getting a p-value that does reject. So in our situation, what would that mean? For a flu vaccine, what if we made a larger alpha level? What does that mean we're considered doing there? Well, in this case, it means that we are lowering the efficacy rate that we would deem especially effective. We're going to use that phrase again. So lowering the efficacy rates that we sort of use as our cutoff here. Okay, so that would mean that we're not going to accidentally fail to reject. If we accidentally fail to reject, so we fail to reject the null hypothesis, meaning we don't have evidence to think it's not true, but we were supposed to reject it, then that's a problem, because then we have a vaccine that we think is ineffective, but it actually was effective. So that's going to be really a missed opportunity there. So here again, we got our little graphs here. We are null centered at 45% in both cases. And on our other side here, we've got in this case, since it's a type 2 error, it's important to think about the hypothetical, where is it actually centered at? And so the actual sampling distribution, the true center, is at 58%. And so we can see that if we set the bar at a level of 5%, alpha level 5% here, just like above, that we have a very, very small blue area there, chances of making a type 2 error, but it's still going to be bigger than if we were to move the alpha level to 10%. So there we have a type 2 error in blue. See how tiny that is, but we had to raise the level up to an alpha level of 10%. Notice how the yellow area got bigger there. So what's the consequence of this? You probably knew this already based off of what you're noticing, but by raising our alpha level, we are now embiggening our chances of making a type 1 error. So you can see that there's not some easy fix here. You can't just go like, oh, I'll just mess with alpha to make it this way, because by sort of shrinking it or increasing it, it plays with both of the types of errors. There's no way to make both error types just go down as small as possible to 0. There's always this trade-off. And so that's the struggle between type 1 and type 2 errors, okay? Because as you decrease the chance of one type of error, you increase the chance of the other. That's the trade-off here. They're a yin and yang, if you will. So now there is a way to sort of get around this, which is a different lesson. We're not going to talk about this today, but I do want to end this video notes with thinking about, is there opportunities where you know that one of the errors is worse? Because if that's the case, if you walk into it knowing, ooh, if I made a type 1 error here, that would be awful. Type 2, whatever. Then you do have some sort of control over this. If you can reduce both, that would be great, but we now know that you can't do that. So which error type is worse? Well, that really often depends on the context. So let's look at a context and sort of see if we can determine whether there is one that is worse. And I'm going to leave this one up to you after we sort of set this up here. So let's consider a very common thing right now. Take an at-home COVID test, okay? So let's define the hypotheses first. We'll just do it in words. We're not going to worry about symbols and stuff like that. So when you take a COVID test, what is the null hypothesis and what's the alternative? Think about that for a moment. So the null hypothesis is you don't have COVID. That would be sort of the status quo, right? I mean, you might be taking it for a reason because maybe you're feeling some symptoms, but that's sort of the idea, is that the status quo, the no change is that you don't have COVID. But on the alternative there, perhaps you do have COVID. Cool. So what I want you to do is describe for me a type 1 error and what are its consequences, a type 2 error and its consequences, and then I want you to think about which one do you think is worse and why. And then because of that, what would you set alpha to? Because of which one you think is a more serious scenario, a more serious error, what would you set the alpha level to? And again, why? You should be thinking about those. There's not space to write the why, but make sure you think about that because these will be things and conversations you'll have with a partner in class. I want to end though really quickly with the notes. So while there are these two different types of errors, there's only ever a possibility to make one of them, okay? Because the whole idea, I'm going to rewind all the way back to the very beginning. The whole idea is that it depends on what decision you have made. So if you have rejected the null hypothesis, the only type of error you could make there is a type 1 because that's the one where you falsely reject. So if you reject, then you either did so correctly or perhaps you made a type 1 error. On the flip to that, if you failed to reject, the only error you could have made is the type 2 type because that's part of it, is that you have incorrectly failed to reject. So there you have it. That is our hypothesis test error notes. Come in ready to talk and think about these things and work through them, and we will see you in class.